In this video, we're going to briefly discuss how to construct a grouped frequency distribution. So one of the first questions we need to answer is what exactly is a grouped frequency distribution? A grouped frequency distribution is going to be a frequency distribution table where we group the data into different classes or groups in order to simplify the tabular presentation. So when would you construct a group frequency distribution? So when we have a numerical or quantitative data set like this, we're going to construct a group frequency distribution when the range of your data is pretty large, as well as the number of observations in your data set. And when you have those two components, when you have large data sets with a relatively large range, it means that you cannot create an ungrouped frequency distribution where we summarize the distribution of each specific numerical value. There's simply the range of the data is too broad in this case to do that. So the first step in creating a grouped frequency distribution is determining the range of your data. So in this case, it's going to be the largest observation minus the smallest observation. And there's actually more than one zero in this particular data set. So our range for this data set is going to be 93 minus 0, which is 93. The second step in creating a grouped frequency distribution is determining the class width of each one of the classes you're going to use to categorize the data. So the width is going to be 93, the range, divided by the number of classes. So in this example right here, we're looking at the number of unhealthy days in selected cities. So we have the number of unhealthy days in these various places. And we want to construct a frequency distribution with 7 classes. So we're going to take the range and we're going to divide by 7. And if we do that, then we get a class width of about 13.3. One of the key details when you're constructing these group frequency distributions is that your class width should match the number of decimal places in your observed data set. So you notice that in this data set right here, there are no decimal places. All the data are in whole numbers. And when we look at our class width here, we always round it up to the same number of decimal places as the data. And since we don't have any decimal places in our data set, we're going to round up the class width to 14. So I say to the same number of decimal places as the data because if, for example, we had data that was something like 13.5, 14.6, etc., and our class width was 2.123, then we would round that up to 2.2. Okay, because the number of decimal places, these values right here have one decimal place, and so we want to round this decimal place up one value to 2.2. So that's a random example. We're just going to erase that so we can forget about it. So we round the class width up to the same number of decimal places as the observed data. So now that we have our range and our width computed, we can now start determining the class limits for our various classes. Generally, the very first class has a lower limit equal to the smallest value in our data set, which in this case is 0. So the lower class limit for the first class is 0. And the way that we get the other subsequent class limits is by adding the class width successively to the lower class limit from the previous class. So since the lower limit of the first class is 0, the lower limit of the second class is going to be 0 plus the class width, which is 14, which gives us 14. For the third lower class limit, we're going to take the previous class lower class limit, which was 14. We're going to add to that the class width, which is 14, which gives us 28. And we keep adding 14 to each of the previous lower class limits to get our subsequent lower class limits. So 28 plus 14 is going to be 42. 42 plus 14 is going to be 56. 56 plus 14 is going to be 70, and 70 plus 14 is going to be 84. So now we need to figure out what the upper class limits are for each class. And basically what you want to do is you want to take the lower class, you look at the next class ahead of you, and you're going to subtract one unit from the next class. So we have 14 right here. If I subtract 1 unit from that, I'm going to get 13. So the upper class limit for the first class is 13. If I subtract 1 unit from 28, I'm going to get 27. If I subtract 1 unit from 42, I'm going to get 41, and so on. The other way of doing this is that once you find the very first upper class limit, you can once again simply add the class width to each of the subsequent upper class limits. So if you notice here, if we have 13 and we add the class width of 14 to it, we get 27. If we take 27 and we add 14 to that, we get 41. If we have 41 and we add 14 to that, we're going to get 55. 55 plus 14 is going to be 69. 69 plus 14 is going to be 83. And 83 plus 14 is going to be 97. So now that we have our class limits, we need to compute the class boundaries. So you may remember when we described the frequency distribution that we need to make sure that there are no gaps between the classes. And if we look at the class limits that we've created, there's gaps between each of the classes. So there's clearly a gap between 13 and 14, between 27 and 28, etc. And so we need to figure out essentially the midpoint between the different classes, and those are going to be the class boundaries. So the class boundary between this first class and the second class is going to be the average or the midpoint between 13 and 14. So the upper class boundary is going to be 13.5 for the first class. And the lower class boundary of the second class is going to be 13.5. And the reason is because they're going to have to share a boundary, right? So if we have 13 and 14, the midpoint between them is going to be 13.5. And that's going to separate the first class, which runs from 0 to 13, and the second class, which runs from 14 to 27. So we have our class boundaries, our upper class boundary and our lower class boundary for the first class and for the second class. And we can keep doing that for subsequent classes. So for the second class, the upper limit is 27. For the third class, the lower limit is 28. The midpoint between them is going to be 27.5. So 27.5 will be the upper class boundary for the second class, and will be the lower class boundary for the third class. And we can keep doing the same pattern here. So the midpoint between 41 and 42 is going to be 41.5. So the upper class boundary for the third class is 41.5. The lower class boundary for the fourth class will be 41.5. And we continue this pattern here. So this upper class boundary is going to be 55.5. That lower class boundary will be 55.5. We move up to 69.5 and 83.5. And you may ask yourself, well, how do I get this very first lower class boundary and this very last upper class boundary, because I don't have any more categories where I can average the limits to get a midpoint? Well, in fact, if you look at this pattern here, all we're doing is we're taking the previous class boundary and we're adding 14 to that. So 13.5 plus 14 is 27.5. 27.5 plus 14 is 41.5. 41.5 plus 14 is 55.5, etc. So if we go down to 83.5 here and we add 14, we're going to get 97.5. And what number, if we add 14 to it, gives us 13.5? Or in other words, what is 13.5 minus 14? It's going to be negative 0.5. So that's the lower class boundary for the very first class, negative 0.5. Another way of thinking about this when we're creating these class boundaries is essentially we have to add one decimal place, and then the decimal place we add is usually going to be 5. And so when we look at this right here, so we see that our class limit was 13. We add a decimal place with a 5, and we get 13.5. For 27, we add a decimal place, and that decimal place is going to be 5. We get 27.5, etc. It gets a little bit confusing with this negative value, but you can see the pattern fairly clearly. Once we have our class boundaries, then we can start to tally the various observations in the different classes. So what that means is that I start looking through my data and putting each observation in one of these different classes. So for example, the first observation here is 61. And so 61 belongs in this fifth class right here. So I'm going to put a 1 right here, or a tally mark, I should say, for that particular class. I'll scratch off 61. Now I'm going to go to 88, and 88 is in the final class. Put a tally there, cross off 88. 40 is going to be in this class right here, so I put a tally mark right there. 5 is in this group right here. 12 is going to be in the first class again. And so I start doing all these tallies, and I go through, I'm going to do that for every single observation. And once I do that, I'm going to add up the number of tallies in each class. And if I do that, I would find that the number of observations in the first class is 14. The number of observations in the second class is going to be 9. The number of observations in the third class is going to be 5. Then I have 1, 1, and 1. In the next 3 classes, and the last class is going to have 2 observations. You have to go through the entire data set in order to do that computation, but it just takes time to do that. Once we have tabulated the frequency in each class, we want to compute also the cumulative frequency. So the cumulative frequency takes the frequency of the current class and adds to that the cumulative frequency for the previous classes. So for this very first class, there are no previous classes, so the cumulative frequency is 0. And we add to that the current frequency of 14, and we get 14 plus 0 equals 14. To get the cumulative frequency for the second class, we take the current frequency and we add the previous cumulative frequency to that. And so we get 9 plus 14 equals 23. To get the third cumulative frequency, we're going to add 5, the current frequency, to the previous cumulative frequency of 23 to give us 28. And then I'm going to keep going with that same pattern here, and I'm going to get 29, 30, 31, and 33. And one thing to note is that once you've added the cumulative frequency for the final class, the total cumulative frequency should match the total number of observations on our data set. And if you look across this data set, there's 11 observations in each of the 3 rows. 11 times 3 is 33, so there are 33 observations, which does in fact match the cumulative frequency for our final class. And so that gives us some confirmation that we have in fact done our computations correctly.